Take a moment to think about how much you've inherited from your parents. There are many things that make you unique, from the environment you grew up in to the experiences that you've had. But the vast majority of things that you probably take for granted, from the proteins formed in your cells to the way the cells join together to make tissues and organs, to the most fundamental ways that your body works, are all inherited. For the past 3 lectures, we've been using encapsulation, what I described as the most important idea of object-oriented programming. Encapsulation is the wrapping of data and functions together in one tidy package. Well, now we're going to explore another powerful idea called inheritance, which is the idea that we should be able to create classes that can inherit this encapsulation of member variables and functions from another class. In short, we can use an abstraction that we already have to create one or more new abstractions. And this creates a hierarchy of sorts. Objects can inherit from a parent, and the relationships among various inheriting objects can form a tree structure. Inheritance gives us several benefits, which is one of the reasons that inheritance became a core part of object-oriented programming. For one, inheritance prevents having to rewrite the same code over and over. An ancestor can pass on properties to all of its offspring. In terms of coding, this can save us a lot of time and work. Inheritance also reduces the number of places that bugs could be introduced to the program, so we reduce debugging time as well. And inheritance will enable polymorphism, which we'll learn about next lecture. In practice, there are a couple of ways that inheritance works. From a top-down viewpoint, object-oriented inheritance can be thought of as a way of taking a more general idea and specializing it. We can take a broad class of objects, like vehicle, and break it into more specialized classes, like land vehicles, air vehicles, and sea vehicles. Each of those could be further broken down into even more specialized classes. Land vehicles could be divided into, say, motorized and non-motorized vehicles. And then motorized land vehicles could be subdivided into cars, trucks, and motorcycles. So, top-down involves taking a more general idea and dividing it into more specialized classes. But inheritance can also work from a bottom-up viewpoint. From this perspective, we start with the offspring, and we decide what sort of ancestor they have in common. For instance, imagine that you had a business, and you had a class for each of the products that you sold. Although different products will have some different characteristics, they'll all share certain characteristics, like the wholesale cost you paid and the retail price you're charging. So, rather than defining wholesale price and retail price for each of them, you could instead define a single class that handled wholesale and retail price, and then every product could just inherit from that one class. So, bottom-up involves taking multiple ideas and extracting from them common ideas. Whether top-down or bottom-up, the end result is a similar arrangement of classes. There are actually different terminologies that are sometimes used to describe the relationships between different classes in a class hierarchy. First, following the terminology that we use for trees, we may refer to a parent class and a child class. One parent can have several children, also known as offspring. Another terminology that's used is superclass and subclass. A superclass is the class above a point in the hierarchy, and a subclass is a class below a point in the hierarchy. A superclass encompasses lots of different classes, and a subclass is a more narrow description of a class. And a third terminology is to talk about a base class and a derived class. The base class is effectively the parent, and the derived class is the child. So, for the most part, if you hear the term parent class, superclass, or base class, those terms probably mean the same thing. And if you hear the term child class, subclass, or derived class, well, those terms mean the same thing. We've already seen a couple of areas in which inheritance is used to define classes. One important area involves streams. We've seen streaming to and from the console, and we've seen streaming to and from files, and we've seen streaming to and from strings. All of these are basically derived classes that inherit from a more general stream base class. A second area of inheritance that we've already encountered are exceptions. Exceptions are used to cause a function to exit when an exceptional case is encountered. There's a very general exception class, and then more specific child classes like logic error and runtime error. Then each of those has further, even more specialized classes. Logic errors have child classes like invalid argument and out of range. So, an out of range error will inherit the logic error properties of its parent, which in turn inherits the general exception properties. Let's look at an example of how inheritance works. In this example, we have a general class, the product. Products contain floating point member variables for both a wholesale cost and a retail cost. Then there's a separate class created for a more specific product, the cup. The cup has two member variables of its own, a volume that the cup holds and a color for the cup, represented as a float and a string respectively. Now, the key difference here from what we've seen before is that the cup is also defined to be a child of the product. And we see this by the :public product placed right after the class name. Since this is the case, the cup inherits the member variables from the product class. Then, in the main routine, we can define a cup object, which we name plastic cup. This will let us set not just the volume and color, but also the wholesale and retail costs for the cup. And we do this by assigning values to plasticcup.wholesaleCost and plasticcup.retailCost, the same as we would the other member variables, plasticcup.volume and plasticcup.color. Let's look at the syntax for inheritance just a little closer. At this point, to keep things simple, let's assume that everything is public, and I'll explain the alternatives in just a moment. When creating a class, if we want to inherit from some other class, we declare the class like usual, but we have a colon, an access statement like public or private, and then the name of the parent class. In the example we saw before, we wanted to create a cup class that was derived from the product class. So we would write class cup :public product, and then the class definition in curly braces. Now, we can inherit in a larger class hierarchy. For instance, say that we wanted to further distinguish our cups so that some of them were specifically measuring cups. We could make a new class, a measuring cup class, and it would inherit from cup. So we would write class measuring cup :public cup in the declaration. And that means that it inherits the features of the cup class, which therefore means it also inherits the features of the product class. It can also define its own member variables and functions. So in this case, we can define two new variables for the measuring cup: a Boolean to note whether it's in metric or English units, and an integer number of gradations. So thus, a measuring cup actually has access to 6 different member variables: the 2 that it defined for measuring, the 2 that were defined in the cup class, and the 2 that were defined in the product class. And, just as we'd expect from a hierarchy, we can have more than one derived class from the same base class. For instance, in addition to a measuring cup, we could define a drinking cup. In this case, I've defined it as a subclass of cup with one more member variable, a Boolean denoting whether it has a lid or not. Now, just to be clear, inheritance only goes one way, from the parent to the child. A superclass does not have access to the member variables and functions of the subclasses, and sibling classes don't have access to each other's variables. For example, what happens if we have our class variable product and we declare a new object within the class, sale item? So sale item cannot access member properties that were declared in the cup subclass, like volume, or in the drinking cup subclass, like has lid. Likewise, if we have an object styrofoam cup that's a drinking cup, we can't access member properties of measuring cup, like metric units. We'll get an error if we try. Okay, let's try a quick check to see how well you're following. Let's say that in addition to cups, you wanted to sell plates. See if you can create a new type of product, a plate, that includes a diameter measure. Okay, here's one way that could have been implemented. We declare a class plate that inherits from product by writing class plate public product. And inside the definition, we declare a member variable named diameter of type float. That's all there is to it. We're not confined to inheriting just member variables either. We also inherit member functions. So, say our product class had a member function named profit per unit. It would be a simple function, just returning the difference between the retail and wholesale prices. Then, if we have an object of some derived type, like a measuring cup, we can call the function on the measuring cup just like we would for the base class. In the example here, we're able to have a measuring cup object named plastic cup, and we call plastic cup dot profit per unit to get the profit. Now, up until this point, my examples have had all of our member functions be public. But as we discussed back when introducing the idea of encapsulation, the idea of information hiding, of not allowing outsiders access to more information than they need, is important to creating good classes. It helps ensure that a class's member variables are only modified in approved ways. And so, we declare some member variables as private and some as public. Well, when it comes to inheritance, there's actually a third category in between public and private called protected. Now, as before, things that are public will get inherited by all of the descendants and be public members of all of those descendants. Any code can call those member functions or access those member variables directly. The private member properties are accessible only to the class that they're declared in and no others. Not even the descendants of a class can access those member properties that are considered private. So, although the descendants still inherit those variables and those functions, that is, they still allocate space for those member variables, and they can have values stored there, they can't actually call the private functions or read the private variables defined in an ancestor. And this is why we have the protected category, which falls in between public and private. Protected member properties are accessible to the class that they're declared in and to the descendants, but nothing outside. In effect, this is like a private member property for everything following in the inheritance tree. You can think of these kind of like you might think of things in real life. There are private things that you probably think about but you don't share with anyone else. And there are protected things that you might talk about in your own family but that you don't talk about to those not in your family. And there are public things that you just discuss with anyone. Let's see an example of how the protected category of inheritance works. I'm going to create a bank account class that can be used to keep track of different bank accounts. We'll have a base class called bank account and two derived classes, checking account and savings account. So first, let's look at the class declarations. We have the bank account class declared just like any other class. It's not inheriting from anything. Within the bank account class, we'll have three groups of member properties. First, we have private member properties, which in this case are the owner name, the owner address, and the account number. Because these are private, that means that the derived classes, which will be checking account and savings account, will have access to those member variables, but they won't be able to access them directly. The only way they'll be able to access these variables is indirectly through a member function inherited from bank accounts. and no other classes outside a bank account will be able to access them directly either. So, we've got a couple of members that are declared as protected. There's a protected variable, a double precision floating point number named balance, and there's also a protected function, a set account function, that sets the account number in the balance. Now, because the balance variable and the set account function are protected, any subclasses that we might define under bank account will be able to access them. That is, the subclasses will be able to modify the balance directly, and they'll be able to call the set account function. But no other classes and no code outside of the bank account subclasses will be able to access these protected variables or functions. So no outside code can call set account, and no outside code can look at or modify the balance. And then we've got a couple of public functions, which are functions that we might need to be able to call from the rest of the program. And one of these lets the account name and the address be changed. The other one prints out the account information. And notice that since both of these are public, they can be called from anywhere. Any other code from any class or function can call either of these two public functions. Now that our bank account class is all set up, we can turn to subclasses. Let's suppose we have a checking account class and a savings account class, each of which inherits from bank account, as specified with the :public bank account designation. First, let's look at a way to implement the checking account, which has a few public functions. Remember that public functions are the things that might need to be called from outside the class. One of these, begin account, is used to indicate that a new account is starting. So it just calls set account. Since begin account is part of the checking account class, and the checking account inherited from bank account, it's able to call the set account function that was a protected function of bank account. Checking account also has functions to deposit and withdraw money, and each of these refers to the protected balance variable that's inherited from bank account. And again, because this class inherits from bank account, it can access the protected member properties. Now in the savings account class, there's a private member variable interest rate. Remember that for classes, if we don't declare it as public, private, or protected, it's assumed to be private. But just to be especially clear, we'll explicitly declare it private by putting private : beforehand. We also have two public member functions that we might want to invoke from outside the class. These are begin account and generate interest. And like the checking account, these access the protected function set account and the protected variable balance that are inherited from the bank account. If we then in our main code want to work with some individual's accounts, we can declare both a checking account and a savings account object for that person. In this case, we have accounts named Holmes Checking and Holmes Savings, and we can call any of the public member functions on them. So, we can call begin account defined in the checking account or the savings account class. We can call deposit and withdraw on the checking account, or generate interest on the savings account. Or we can call update owner and print account functions that were defined in the base class bank account. All of this runs fine. Within any class, we're accessing only functions and variables that were either defined in that class or were public or protected properties from an ancestor. And from outside the classes, we're only accessing public properties of the class. Now, just to illustrate, there are several things that we would not be able to do. We could not access a private member variable of the parent class. For example, trying to access the account number directly from within a checking account generates an error. And we could not access any private member function from outside the class. For instance, we could not access the balance from outside the class definitions. Okay, let's talk about one other thing we need to handle when using inheritance. That's constructors. If you look at the examples we've seen here for products and bank accounts, You might have noticed that constructors have been missing so far. Well, for the most part, constructors work much like all the constructors we've seen before, but it can be a little tricky to handle constructors when you're inheriting some of your properties and you don't have direct access to them. The way to think of this is that when you call a constructor in a derived class, you need to first have a constructor for the base class. After all, the derived class is only adding additional stuff onto whatever was already in the base class. So, first, you need to have the base class set up, and then you can add on whatever additional things are needed for the derived class. The way this is done is that when a constructor is defined, we put a colon after the constructor declaration, giving the constructor to use for the base class. Here's an example where we're using the bank account classes that we saw earlier. For the base bank account, we'll define two constructors. First, we'll have a default constructor that basically sets everything to empty strings or the number 0. Then, we'll have a constructor that takes in all the various parameters needed to initialize all the member variables to specific values. In this case, there are 4 parameters for the owner name, owner address, account number, and starting balance. We use these parameters to initialize the various member variables of the bank account class. All of this is just like we would have had for any other constructor. Now, let's look at the constructors for the derived classes, the checking and savings accounts. For a checking account, there are no new member variables. So, the checking account constructor doesn't need to do anything more than call the base class bank account constructor. We define 2 constructors for checking accounts, one default one, and one with the 4 parameters needed to initialize a bank account. For the default constructor, we just write checking account parentheses, colon, bank account parentheses, and then a couple of curly braces with nothing inside. That colon bank account with no arguments in the parentheses means that when this default checking account constructor is called, it will first call the bank account constructor with no arguments. In other words, it calls the default bank account constructor first. There's nothing in the curly braces, so there's nothing more done. Now likewise, for the other constructor, we'll call the bank account constructor with 4 parameters. Again, there won't be anything in the curly braces. We just define the checking account constructor to take in 4 parameters, and then we write colon bank account, and in the parentheses, we pass those same 4 parameters as arguments to the constructor. This will call the non-default bank account constructor with those arguments. And then we would do whatever's in the curly braces, which in this case is nothing. Now with the savings account, there's one more member variable. We'll again define 2 savings account constructors, just like for the checking account. Everything will be the same about these, except that the member variable, interest rate, will need to be set in each constructor. The default constructor just sets this member variable to 0, after calling the default bank account constructor. The other constructor takes in 5 parameters, and it passes 4 of those on as arguments to the bank account constructor. Then it uses the 5th parameter to initialize the interest rate inside the curly braces. We can see that if we declare instances of the checking account and savings account variables with the non-default constructors, we do get everything initialized correctly. The main point here is that when you're defining a constructor in a derived child class, you probably need to make use of the constructor in the parent class in order to fully initialize an object. And in particular, if the parent has any private member variables, the way you'll initialize those is by using the parent's constructor, since the derived class can't access those variables itself. I want to talk about 2 other topics that it's worth being aware of, but that truthfully have only limited usefulness. These are non-public inheritance and multiple inheritance. Now you may have noticed that when we designate inheritance, we always have been putting :public class name for the class that we're inheriting from. We call that public inheritance. And that's the most common way that inheritance is handled, and in most cases when I'm writing code, I find that I want to inherit using that terminology. Public inheritance means that the public, protected, and private member functions are inherited just like you'd expect. But if you're ever in a professional setting needing to develop a library, you might conceivably want to designate the entire inheritance as either private or protected. And private and protected inheritance make the protected and public members that are inherited even more restricted. With private, they're all inherited as private members, and with protected inheritance, they're all inherited as protected members. We use protected and private inheritance as a way of making use of another class for implementation without having to seem like our new class is really derived from it. To get private or protected inheritance, you simply replace :public class name with :private class name or :protected class name when you're declaring a new class. In effect, if it's private inheritance, then no other classes, even descendants, will know that that inheritance occurred. If it's protected inheritance, then only descendants will know that the inheritance happened, but nothing outside will. But the version we've been using, and what I would recommend you continue using, is public inheritance. It ensures that the private, protected, and public members of the base parent class have their expected usage in the derived child class. The other topic that I want to tell you about, but warn you against using, is called multiple inheritance. Multiple inheritance is an idea that in my experience tends to create even more problems than it solves. Now, the idea works somewhat like it sounds. Just as people inherit genetic information from more than one parent, we can have classes that inherit from more than one parent class. But unlike biological inheritance, where each parent passes on half of their traits, in programming, the new class gets all of the member properties of both parent classes. And that's where the trouble starts. For instance, say that we had a color class, and we also had a shape class. Well, we might be able to create a colored shape class that inherits from both of these. And that might seem straightforward. But there are all sorts of problems that might come up in these cases. What happens if the color class has a member variable called name, giving the name of the color? And the shape class also has a member variable called name, giving the name of the shape. In other words, the two parents have overlapping information. They each defined different members, but with the same name. Well, the colored shape will then be trying to inherit two variables, both called name. And you can't have two member variables with the same name. Or, as another example, what if both parents actually inherit from some common ancestor themselves? This is a bit like two cousins getting married and having children. For example, what if there were a base class kindergarten terms that defined name and both color and shape were children of kindergarten terms? Well, both color and shape would have inherited name from kindergarten terms. And then colored shape would again be trying to inherit two versions of name, even though there was really just a single common ancestor that defined it. Now, there are actually ways of resolving all these potential conflicts, and C++ has a clear specification for how that happens, but it can get complicated. There's even examples where multiple inheritance is clearly useful. Streams is one example that we've seen. There's a large class hierarchy of streams, starting with a base iOS stream. Then there are output streams, or O streams, and cout is an example. And there are input streams, or I streams, like cin. And then you have IO streams that inherit both I streams and O streams. And both the F stream and the string stream, for strings, inherit from IO streams. They can handle both input and output. But that's the exception. The truth is, there's normally no need to use multiple inheritance. Having to deal with all the issues and weird cases that multiple inheritance raises tends to outweigh the benefits that it provides. Before we go, let's try one more example of ordinary, non-multiple inheritance. Say you owned a store, Everything Wrists. that sold wrist accessories, bracelets, watches, fitness trackers, navigators, rubber wristbands, bandanas, rosaries, and so on. You want to keep track of your products, so you'll put together some classes that can be used to describe products. First, can you think of the classes you might want, including which ones might inherit from others, and what data that each class might contain? Well, one option might be to have a base accessory class that includes a cost and a sale price. Then you could have subclasses for bracelet, watch, wristband, fitness tracker, and so on. The bracelet class might include a material, a clasp type, and a size. And the rubber wristband might include a color and a message, and so on. You could come up with lots of data and lots of ways to organize this, I'm sure. Now, how might you go about implementing a couple of those classes? Say the accessory base class and the rubber wristband subclass. Well, first you would declare the accessory class. It would need to have a couple of member variables, one for cost and one for sale price. And it would be a good idea to have constructors, both a default constructor and a non-default. Then you'd declare rubber wristband as a class that publicly inherits from accessory. This class would have another couple of member variables, one for the color and one for the message. And likewise, we'd want both the default constructor, which would also call the default accessory constructor, as well as a non-default constructor that likewise called the accessory non-default constructor. So, in our main function, we could easily declare examples of type rubber wristband. Inheritance plays a powerful role in object-oriented design. It lets you define something a single time in one class and then use it in multiple other classes. And it means that you can define a new class, and rather than writing every piece of it from scratch, you can start with everything you already defined in another class. And inheritance creates a hierarchy of classes, a relationship between ancestors and descendants. In the next lecture, we'll see how the properties that each child inherits can be configured much more flexibly using a virtual function, which is the basis of another object-oriented technique known as polymorphism. See you there.